Hello and welcome to the fifth video of the FP3 chapter Integration. Question on the screen: if you've got time, pause the video now and see if you can do this integration. To do this, we're going to need to remember how to integrate by parts. And that's using this formula in the formula booklet. But this is usually applied to a product, as you can see here, something times by something. So there's a sneaky trick. In order to do this, we can consider this as being 1 times log of x. And then to integrate this by parts, we can choose the log of x to be our u in the formula, and dv by dx to be just a 1. So when you integrate that, you get x, and when you differentiate this one, we get 1 over x, and then we apply the formula. So we have u times v, so x times log of x minus the integral of v times du by dx, which is 1 over x, which of course cancels to give us just dx, which integrates to give x plus c. So this is a nice trick. I hope you've come across this idea before, where even if you don't have a product of two things, you can consider one of them to be a 1, and then apply it as normal. And we're going to use this process in this video to integrate by parts, specifically inverse trigonometric and inverse hyperbolic functions. So we're going to do the same thing on a couple of examples in this video, and you might expect that as you apply this formula, this integral here might then lead on to one or other of the different techniques that we've looked at so far in this chapter. So don't be surprised if you have to do this and then also do something else that we've done. And that's it, that's the notes. We're going to do the same process using dv by dx equals 1. I'll just go through a couple of examples to show how this works. First one, r tanh x. Again, let me put down here, we're using dv by dx equal to 1, so v is equal to x. Then u is equal to r tanh x. And we need to differentiate that. So if you can't remember, we can use the formula booklet, and r tanh, if we differentiate that, we get 1 over 1 minus x squared. So our integral, if we apply the integration by parts formula, we get u times x, so x being v, sorry, u times v, so we get x r tanh x minus the integral of v times u, so that's x, times 1 over 1 minus x squared. And then to integrate this, hopefully you've done enough practice by now, you can see the thing on the top of the fraction is the derivative, or close enough, of the thing on the bottom of the fraction. We need a minus 2 to get that right, but I can just put that in. Let me put it in green. No, I won't. I will leave it. I'll do it in the next one. The next step. So we've got x r tanh x minus the log of 1 minus x squared, and this is where I'll put it in. If you were to differentiate this, you would have a minus 2x over 1 minus x squared, but we don't have a minus 2x, we just have an x. So I need a minus half. So that will become a plus, and there will be a half here to cancel out that minus 2 because it wasn't here. And then of course I should put a plus c on the end. Now that was not too bad. It's only a couple of lines of working, but they can get more complicated. Second example is to evaluate this integral, and we're going to do the same thing. So we've got dv by dx is equal to 1, v is equal to x, u is equal to arc sine x, so du by dx is equal to the derivative of arc sine, which is 1 over square root of 1 minus x squared. So applying the integration by parts formula, we have u times v, x times arc sine of x, minus the integral of v times du by dx, x times 1 over the square root of 1 minus x squared. But because we are trying to evaluate this, we're putting numbers in, this is a definite integral, we need to evaluate this at those limits and integrate with those same limits on this integral here. So if I put that in, root 3 over 2 in here is just root 3 over 2, but the arc sine of root 3 over 2, I'm going to need my calculator, is pi by 3. So we've got root 3 over 2 times pi by 3 minus a half in there, and arc sine of minus a half. Arc sine of minus a half is minus pi by 6, so the two minuses cancel out and it's still a minus here. And we've got 1 over 2 times pi by 6. So this is a minus from when you are substituting your limits in. You do the upper limit minus the lower limit, and then we have another minus from this, but then we have a third minus from this, so overall we've got that minus still there. And this is the limits just for this section here. We still need to integrate this and put the limits in here. So the integral here, what I might have been better off writing that as this, because then it's a little bit easier to see how we're going to integrate this. The thing outside the brackets is very close to the derivative of the thing inside the brackets. So this is probably going to be the answer to the derivative of 1 minus x squared to the half, or something like that. Because if I differentiate this, the half comes down the front, we get a minus 2x out of the bracket, and then the bracket matches, the half and the 2 cancel, so really the only thing that's missing there is a minus. So that's pretty close. So we've got 1 minus x squared to the half. And as I just talked through there, if you try to differentiate this, you get very close to this, except that there should be a minus in front, so I need to balance that by putting that minus there to a plus. We don't need the plus c in this case because we are putting in limits, but we do need to go ahead and do that. So over here we've got root 3 pi by 6 minus pi by 12, and then if I put the limits in here, let me just think this through, I might not need a calculator because squaring that will give me 3 over 4. 1 minus 3/4 is 1/4, and the square root of a quarter is a half. Minus a half squared is a quarter, 1 minus a quarter is 3/4, square root of 3/4 is root 3 over 2. And I don't need those big brackets there. That is my answer. I could maybe tidy that up a little bit, but actually what I'm going to do is, if it needed to be exact, I would probably combine these two into one fraction, which is very easy, 1 minus root 3 over 2, and then I would probably leave it, possibly combine these two into one fraction because they both have pi's. You could probably combine all of them into one fraction if you were so inclined, but none of that is really simplifying it as such. So this is exact, but if you put all of that on your calculator, you would get the answer 0.279 to 3 significant figures. And depending on what the question wanted, you could put it exact or you could put it into decimal form. So that one is a little bit more complicated, but I hope you can see that these could become very complicated if this integral, once you've done the integration by parts line, if this then needed you to do a substitution, for example, this could be quite a complex integral in its own right. So this question could become quite involved. But that should be enough to practice this idea using integration by parts with dv by dx equal to 1 from exercise 4E in the textbook. And maybe I'll see you in the next video.